up, guys? Welcome back. Hope you guys are doing well. Happy Friday. All right, so geometry, you guys are starting a new chapter, chapter 11, so I'll put the link to the notes in Classroom. Make sure you download it, print it out if you can, and fill it out. Algebra 2, you guys are going to continue on in chapter 4, so make sure you guys are taking good notes. Now, both classes, you guys have a quiz next week, so if you have any questions about preparation or what to expect, make sure you email me, and then if you need extra help, we can do a video chat if you want. Yeah, that's it from me. Enjoy the lecture. See ya. Alright, so today we're starting a new chapter. We're going back to chapter 4. We're starting with section 4-1, exponential functions, and we're going to be looking at growth and decay. So today, 4-1a, new section of notes, we're going to be looking at how we actually graph these exponential functions, determine if we have growth or decay when looking at the actual equation given, the function given. Before we get into that though, let's do a quick review. Make sure you remember how to solve something like this. Let's say I have 2 raised to the negative 2, so we have a negative exponent here. What do I do in this situation? Well, remember, a negative exponent, that means I flip the number here. So if it's on top, it goes to the bottom, bottom goes to the top. So this would be 1 over 2 squared. Now my exponent is positive. Well, 2 squared is 4, and that would be my answer. What if I had something like this? 1 over x to the negative 3. Well, since it's on the bottom, negative exponent, I flip it, it goes to the top, I just get x to the power of 3. So we'll be using that. Just remember that's how that works. But now let's go and look at the actual exponential functions. So say that we had, just as a introductory example, let's say that you had this information where you had certain years, and every single year we have a certain amount of transistors that are produced. So in 1965 we had 60, 1966 there's 120 transistors, 67 to 40, and so on. Well, what is the relationship between the transistors produced every single year? How to get from here to here? Well, hopefully you see that every single year the number of transistors is doubled. So this would be an example of exponential growth, an exponential function. So here, growth that doubles every year can be modeled using a function with a variable as the exponent. So that's the key. An exponential function is where the variable is in the exponent. The exponent is the variable. So this function is known as an exponential function because the variable is in the exponent. Now the parent function is this right here. So this is the parent exponential function. And notice that our exponent is the variable. The x is in the exponent. And then this number here is what we call the base. That's the number that that's being raised to the variable of x. Now a few things we do have to make sure of. Our base right here has to be greater than 0, and it cannot equal 1. That's a few things we have to make sure of when looking at our exponential function. But this is the parent exponential function. So this equation here, this function here, that actually models this because every year it's doubling the number of transistors. So when looking at this function here, that would be exponential growth, and we'll explain why in a bit. And hopefully you see kind of the idea that we're increasing in numbers. So we're growing in the amount of numbers, so that's growth. But let's go and look at how we would graph this. We're going to do this by hand. We're going to graph this by hand. So the first thing I'm going to do, I'm still going to create my XY table. Nothing changes there. I'm still creating an XY table. Well, remember, a good starting point for graphing is I always suggest starting at -2, -1, 0, 1, and 2. You can always add points as needed or take away points as needed. But notice, this is my x column. So those values are going to be plugged in to the exponent here. So let's start with -2. So to my equation, I'll just say y, same thing as f of x. So y is going to be equal to 2 raised to the power of -2, right? -2 goes right there. I substitute it for the x. Well, 2 raised to the -2, that's what we just did back there. Right, 2 to the -2 is equal to 1 over 2 squared, which is 1/4. So this will give me 1/4. That's my first y value. So y, when x is equal to -2, is 1/4. Well, now let's start working my way down. And just do this for each question, each number right here. So y is equal to 2 to -1. Well, that's 1 over 2, 1/2. Just stay a little organized. 1/2. Well, now let's look at 2 to the power of 0. Well, anything to the power of 0 is always 1. So I get a 1 as my y coordinate. Let's do 2 to the power of 2. Well, that's just 2. And our last one's 2 squared, which is 4. And let's go one more, just so we can see a little bit more information. I'm going to put a 3 here. Remember, you can always add as many points as you want or take away points if you don't need them. But usually more is better. Well, 2 to the power of 3, right? That's going to be 8. So I have my xy coordinates, and now let's go ahead and plot them. So using my graph, we're going to be graphing our exponential function. My first coordinate is 2, 1/4. -2, 1/4, sorry. So I have -2. I'm going to go up 1/4. So right about, if I can get it, right about there. Next coordinate, -1, 1/2. -1, 1/2. Next we have 0, 1. 0, 1 is right here. And then we have 2, 4. 2, 1, 2, 3, 4. Come on, it's not working. There we go. Sorry. I missed 1, 2. I have 1, 2 right here. Missed that point. And we also have 3, 8. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. So those are the coordinate points that I plot. And then we just go ahead and graph this to kind of get the picture of what this would look like. And that's not the best, but that would be our function graphed. That's our exponential graph there. Now, a few things to note. We do have an asymptote on the x-axis. What that means is that my graph will approach the x-axis and gets infinitely close but never actually goes to the x-axis. It converges to the x-axis but never actually crosses it. So we have a horizontal asymptote right there, but this is our actual function. So that is how you would graph by hand, making an XY table. Well, this models exponential growth because, again, let's say that x was equal to time, because with our exponential functions, this is really practical in everyday life. This is one of the most practical, I think, out of all of that we go over, because this applies to finances, it applies to a bunch of different areas of life that actually come into play. So let's say that x was our time. Let's say that, so if the x-axis represents our time, and let's say y is the number of transistors, because we're graphing this. So y-axis is the number of transistors. Notice that as our time increase in time, there's also an increase in the number of transistors produced. So as time increases, the number also increases. That would be exponential growth. So our exponential growth function looks like this. A few things to look out for is that our base here is going to be greater than 1, that's the key. And then a, if there's a number in front of it, that also has to be greater than 1. So as the function increases, as x increases, this would be an example of a direct variation. As one increases, the other does as well. And usually on the graph, typically, the function will look like this. Well, exponential decay, the function would look more like this. Because if we look at our xy axis, as time, x is time, as your time increases, the function decreases, it goes down. So that would go more like this. So that's kind of what the graph will look like, some version of that. Well, for exponential decay, the key here is that your base, the number that the exponent is attached to, that x right there, that's going to be greater than 0 but less than 1. So if you have a number as the base that is greater than 0 but less than 1, that will be exponential decay. So the function will decrease as x increases. So as we increase our time, the actual function gets closer or gets less. So this is the key. You're looking for the base. Is it greater than 1 or is it less than 1 but greater than 0? That will tell you. So our first example, tell whether the function shows growth or decay and then graph the function. For this one, we're going to make a table. There we go. On the quiz, you will have to make a table on the quiz. So just note that. So right away, we can tell, well, first we have to identify what our base is. What's b equal to? Our base is 1.5. Since that's greater than 1, this would be growth. This model's growth. So my function will be increasing as x increases. Well, to graph this, let me erase some of this. We're going to make an xy table. So I do know I have growth. It's going to make an xy table. Again, start with -2, -1, 0, 1, and 2. So if I plug in -2 for x, I'm going to get 1.5 raised to -2. This would be what y equals. That means y is equal to 1 over 1.5 squared. Well, that gives me, if I convert to decimal, 0.4. Now I keep doing this just for a second. I can do one more. You can use your calculator for that last part. So y is equal to, let me see, 1.5 raised to the negative 1. So that's 1 over 1.5, which converts to the decimal of 0.7. And 1.5 raised to the power of 0 is 1, always going to be 1. 1.5 raised to the power of 1 is 1.5. 1.5 squared is 2.3. So there are my xy coordinates. And now let's go ahead and plot these. So I get negative 2.4, that's right below a half. I have negative 1.7, negative 1.7, that's right about here, just kind of estimating. I have 0, 1, it's right here. And then I have 1, 1.5. And then I have 2, 2.3. And then if we keep going, you could add points if you want to. I added a few more. 3 goes to 3.4, 1 to 3.4, right about here. And I did 4, that's 4, 1, 2, 3, 4, 5.1. So our last coordinate here is 4, 5.1. Well, that gives me this type of graph. Let me try that one more time. And that shows growth as we predicted. So as your time increases or whatever you're looking at increases, your function also increases. All right, let's do another one. Tell whether the function has growth or decay, and we're going to be looking at the function, what do I have? G of x is equal to 30, 0.8 x. So that's the function that we're looking at. Now what's my base? What's b equal to? Well, b is this right here, because the exponent is attached to the 0.8, so that's what my base is. Now that's less than 1, so this would show decay. So the graph should look something like this. But let's go ahead and use our graphing calculator to graph this. And then, so let me write the function again. So g of x is equal to 30, 0.8 raised to the x. And then we'll use the graphing calculator. Okay, so to graph the exponential function that we just looked at, we're going to go over to y equals. I'm going to enter the equation, so 30, parenthesis, and do 0.8 raised to the x, close parenthesis. Well, I'm going to push over, go back to the base, now close parenthesis, and then I hit graph. And there's my exponential decay. Now if I want to fit the whole graph into the window, I can hit zoom, and I can hit, let's go with standard first. Doesn't change anything, so let's go zoom, and then if we scroll down, zoom 10 or zoom 0 is zoom fit. So I'm going to hit enter, and there's my exponential decay function. Now if I wanted to look at all the xy coordinates, I could hit second graph, that gives me the table, and that gives me all of the xy coordinates. And notice how when x is equal to negative 10, 279.4, it quickly starts to get lower and lower. And then if I go further out in the x points, I keep getting tiny numbers, 0.001, 8.4 raised to the negative 10 to the negative fourth. So you see that converging to the x-axis. So those are two more examples. We don't have to graph these. Let's just determine whether we have growth or decay from the given function. So example C here, is this growth or decay? Well, what's b? B is 1.2, so it's greater than 1, so this would be growth. Example D, is this growth or decay? Well, what's b? B is equal to 0, so actually since b is equal to 0, it does not, where is it? It does not satisfy the initial, there we go. It doesn't satisfy the initial definition of exponential, so this actually is not even an exponential function. So even though the variable is in the exponent is an x, this is not an exponential function because my base is not greater than 0. So just something to watch out for. Alright, hope you guys liked the lecture. Let me know if you have any questions, shoot me an email, and have a good day.